start that. What? Oh, I guess it's April Fool's today.
I know my sister just did. She just called me and fooled.
I don't have an April Fool's lined up for you. And the mini project is real. Well, remember at the beginning of the term, and you guys said, we can't have a 40% final exam. Can you guys wanted this? Yeah, felt like a good idea, right? Mini project. I'm going to introduce it today, and then we've got some material to get through this week, and then on Tuesday you can come in and we'll work on your mini projects, and it'll be due at the end of that week. Okay, so last week of classes, I know it's busy, okay? But I think you're going to like it. Well, okay, that might be a stretch. What am I going to get you to do? It's only 5% of your grade. All right. And so it's well,
are we writing a song?
All right. What is your final project? I would say the hardest part of your final project, in my opinion, is going to be you have to find a data set. That's kind of difficult, but I'll show you some sources. StatsCan has a ton of data sets available, right? But this way you get to pick a data set that you actually want to work with. Okay? And so I think that's important, right? And then so you can find, oh, now I'm remembering. Did you want to be able to work in groups on the mini project?
Yeah.
So you have to pick a data set or find a data set. That's step number one. And then usually what we do is we collect data because we have a research question. Now we don't have that, and it's too difficult to try to find data to satisfy a research question that you've made up. So we're going to work it the other way, which is a little bit tisk. I shouldn't do that, but we're just learning. And so with your data set, okay, you have to be able to do one of each type of inference question. Okay? And so what do I mean by that? You have to do a one sample proportion hypothesis testing question. Okay? I encourage you to do the confidence intervals, but my focus will be on the hypothesis testing. Okay? And so let's see here. One. Well, I guess I did say the group thing, which was well received. You don't have to work in a group, but you're allowed to. And that might make things a little bit easier. Mini group project. You're allowed to do it individually, but I think it's nice to work in a group. Okay, you're going to find a data set. Now, the thing is, once you have a data set, you have to let me know what it is because I don't want any duplicates. Okay, and so you guys are kind of capable of communicating, but I want to know what data set you're going to use so that I can look at it and, well, know what it is. Pick a data set, or I should say find a data set. Oops, find a data set. No duplicates. Okay. So email me. Yeah, email is best. Once you have picked. And also let me know group members. Should have written this out before. Ugh. Okay. StatsCan has tons of data sets that you can download. Okay. Which is Statistics Canada, I guess I should say that. So some resources that you could check out. Statistics Canada. There's lots of different data sets there, especially water related, if that's something you're interested in, maybe. You are allowed to use data sets that are kind of circling around. So if you have a data set that you're working on, right, or data that's been collected, just make sure that you kind of are actually allowed to use it, right, and share it with me. So there's kind of ethical things, but should be okay if it's just water, right? Usually if it's student data or something like that, then you can't share it with me. You'd have to anonymize it. But Stats Canada, Kaggle is a really fun website to check out. Okay. Anyone heard of Kaggle? Kaggle? So Kaggle hosts data analysis competitions. Okay. And so they've got tons of data sets, and so they kind of host competitions, and there's prize monies. And I should have started the course with that. You guys don't have Kaggle? Could be making money on this analysis. The heck? And so that's a fun place to start. Okay. Usually those data sets can be a little bit more challenging just because, you know, there's like usually $10,000 worth of prize money. And so kind of in that realm. And so they're not the easiest data sets to deal with, but just for fun, go check it out and see what you think. Okay. I encourage you to try StatsCan first. I did find I was poking around to see how feasible it would be to make you find your own data set. And it seems like Australia publishes quite a bit of water data. Okay. And so you can Google your way to it. Or if you have something that you are interested in, right? Yeah.
If you have a question in mind, can you type it in and it'll spit out data?
You could, sort of. So they do kind of classify it. But if you do have a research question in mind, then you can let me know and we can kind of talk about if your data would be able to answer it, right? And I'm willing to be kind of flexible here, right? And so some of the questions that you're going to make up, might be a bit of a stretch, right? That's okay. So find a data set. Kind of fun, kind of hard. It can be both. Okay. I would just say, I know this is so rude, but you can Google your way to data sets. Lots of data sets out there.
there are also lots on Open Intro.
Oh yeah, Open Intro has a ton. Which is the kind of the umbrella of our textbook. So, and they have a ton. Thank you. And they'll be nicely curated, right? Nice and clean and kind of set up for specific purposes. Even R has a lot of built-in data sets. And one thing that I want you to keep in mind, once you found your data set, okay, and as you're picking your data set, I want you to make sure that you're able to create a data dictionary. Okay? And so you have to make a data dictionary, and which means you should have some idea of what all the variables are, right? And so then create a data dictionary. Keep that in mind as you're sourcing data sets. Then, in the data dictionary, so you're going to have your original data set, right? Just like we've been doing, and then you're going to make a copy of your data set and clean it up. I guess I should add that here. Call this, sorry, this is 3 now. Create a copy of your data set and clean it, making note of any changes, right? Any changes that you've made, just like you were doing on those Excel assignments that you've been handing in, right? And so far, everything's the same. And so create a copy of your data set and clean it, making note of changes made. Changes or alterations or anything like that. You want to make sure that your notes make it reproducible. Now, what does that mean? It means that if you hand over your original data set, right, then, or if you tell me, hey, I downloaded it from here, I go download it, then I should be able to follow your cleaning instructions to create the data set that you are using. Okay? That's hard in Excel. That's usually a little bit something that we focus more on in a programming language, right? Make sure that you can reproduce all your changes. I'll make a note here. I should be able to reproduce the clean data set. I'll put this down here. Oops. The clean data set from your notes. Of course, I can just do it, but it has to be from your notes. You've got the, I was going to say the power of the lever. That doesn't make sense. You've got the power of the group. Right. Work together. People have different strengths. You can leverage those. You're going to create a data dictionary, right, in a new tab in your Excel spreadsheet. And I was tempted to make you write a report as well, but I guess I'm only saying that so you know how nice I am when I only make you submit your Excel spreadsheet for the group. That's really nice of me, I think. In your data dictionary, it is possible that you don't know exactly what a variable is, right? That's okay. Just be upfront about that and say what your best guess is. Okay. And so kind of I am going to go ahead and assume that it means this, right? And so if unsure of a variable, state your best guess, but be clear it is a guess. Right, you just have to be upfront about that. Okay. Now for the work. Well, you already know how to do all these things. Okay. That's it. Cute. Yeah, right. In a series of new tabs, okay, you're going to formulate a hypothesis for each type of question that we've encountered. Okay? And so in a new tab, or in a series of new tabs, formulate a hypothesis and test it. For each of the following. One sample proportion. Okay. What does that mean? It means you're going to have to find some categorical variable, right? And you want to compare it to some number, right? Some hypothesized proportion. Okay. And so one sample proportion did that on the quiz. And this was your first time being quizzed on kind of a full hypothesis test and a full confidence interval. But don't you worry about a thing. You get to potentially redeem yourself on the final exam, right? And in this mini project. Right? So not to worry. There's lots more where that came from. Then we move on to two sample proportions, right? What I want you to ensure is that because a lot of the time we sample equal proportions from different regions, for example, and so you don't want to compare equal things. Okay? And so just be aware of that, right? If you get a test statistic of 0, that's what I mean. I don't want to see that. Okay? And so make sure that you have kind of two proportions and you want to compare them, right? How does the proportion of, now I can't remember any of it, meets safety standards compare in these two regions, for example, right? And then we did a chi-squared, or I guess I've already started. Test of independence. Which means you now have two categorical variables and you want to know if they're independent of each other. That might take some work, right? And definitely keep these things in mind as you're finding data sets, right? And so you want to pick a data set that's kind of going to lend itself to all these analyses. Okay? And like I said, I'm willing to be flexible on some of these, okay? Especially the one sample questions. They can be a little bit hard to make up, right? What value do I compare it to? It's nice if you know a value, but you can make one up. That's fine. Okay. Then we moved into one sample mean. Oops. Right? How does the mean, most recently, we looked at the mean dissolved oxygen level. How does it compare to 5? If it's less than 5, then we're in trouble, right? And so means questions require a numerical variable, right? And one sample mean, you want to compare the average to some number, right? And if there are industry standards that you're aware of, right, that might be interesting to incorporate, okay? But not something that you're allowed to make up values, okay? Not in real life, but for me, because it's difficult. Today, we're going to talk about 2 independent sample means. Okay, so now we have 2 groups, 2 means that I want to compare. How do these means compare, right? The average, maybe from West Kelowna and maybe from Vernon or something like that, okay, from 2 regions. So you can leverage these categorical variables and create groups. You're allowed to do that. Okay. And so 1 sample mean and then 2 independent sample means. Because on Thursday, our last section of new material that we're going to cover, I know it's this week, crazy, right? So fun, is paired sample means, okay? And so we have 2 samples, but they're paired. Okay? Usually that would be a before and after study, okay? And so, and if you want to kind of capture within subject variability, then you use paired data. And so paired sample. So this we won't have seen until Thursday. And this is today. So you can kind of keep it in mind as we go through material today and on Thursday, okay? Okay, so, wow, how fun. But that's it. That's all I'm asking of you, okay? I guess so in each tab, okay, I want to see the following. In each tab, include only the data that you're using. That's going to make it easier. That's just to make it easier for me to reproduce your results, but also just makes it a little bit cleaner to look at and to do your analysis. And so include only the data you will use for the question. Okay. Then in a text box, and I prefer the white background. I can't remember who did it first, but it makes it so much easier to read and it makes it look a lot kind of cleaner. In a text box with a white background. Give a short description of the question, okay, the question that you're trying to answer. Okay. So give a short description of the question. I'll put question in air quotes because you're making it up and then you're answering it. But this would be, you know, if you had collected this data, what do you imagine the question, the research question was, right? We're interested in analyzing the mean dissolved oxygen level right? If it's less than 5, then that's cause for concern, right? Then you're going to state your null and alternative hypotheses. State the null and alternative hypotheses. That depends on the question, right? And so you're going to state the null and alternative hypotheses, and then now you're out of the text box, calculate the test statistic. Right, that's either a Z or a chi-squared or a T. And so calculate the test statistic and the p-value. And then in a new text box, right, state your conclusion. In another text box, state your conclusion. You have to cover all 3 parts of the conclusion, right? You have to tell me, okay, what is your p-value, right? Pretend that, so usually a report wouldn't include calculating the test statistic and the p-value, right? And so it would be in an appendix somewhere. And so kind of pretend that I can't see the test statistic and the p-value. So then you have to tell me what it is, right? The p-value especially because we got that from the test statistic. That's why we calculate the test statistic. And so state your conclusion means you have to say what your p-value is. How does it compare to your alpha level, right? Is it less than your alpha level or not less than your alpha level? And then what does that mean in terms of your H naught, right? Your conclusion in terms of your H naught. So 3 parts for your conclusion. Compare the p-value to the alpha level. Then your conclusion in terms of H naught. Do you have enough evidence to reject H naught or do you not have enough evidence to reject H naught, right? And then the one everyone loves to forget, state your conclusion to your client. Conclusion in terms of the question. Right? You stated a question way up here. Okay. Description of the question, and then you're going to answer your own question. Okay. And that's it. Wow. But you're going to do that in each of the tabs. Okay. These questions that you make up, right, require creativity. Right? And like I said, I will be kind of flexible as long as you give me something reasonable, right? And like I said, so on Tuesday next week, you can bring any questions, bring what you've been working on. Hey, can you help me come up with something? I'm really struggling with this one sample proportion. I suspect that's going to be the hardest one. And so, and then we can make something up. Okay? So that's for Tuesday. So in class or Tuesday next week, we will work on the mini project. bring your questions. Well, that looks like a mean smiley. Maybe it is. And then we can workshop something. All right. Any questions about the mini project? When's it due? I was gonna do, you wanna do Friday, the 11th? Last day of classes? I'm not gonna ruin your weekend. So the last day of classes, make it, pull off the Band-Aid. Let's get it over with. Do Friday. Oops. April 11th. At midnight, as always. Well, a minute before midnight. Is that for me?
No, Frank.
Oh.
Figure out when his things actually due.
I think it's next Saturday, 12th, I think.
Yeah, it's a big for 12. Yeah.
Where did you find that information?
I think it's in the outline for the paper.
Well, I'm in there right now and it says April 14th, 2023.
So you have a little bit of a pile up.
But then it'll be almost done by.
Almost there, almost there. You can do it. Oh yeah, any other questions?
Like data sets and more like much possibility.
Yeah, I don't have a minimum size in mind, but you do need to be able to answer all these types. So it's more about the number of variables that you have than the length. Because you want to have enough variables, right? To do a chi-square test of independence, you need to have collected at least 2 categorical variables, right? And for 2 independent sample means, you need at least 2 numerical variables, or at least 1 numerical variable that you can split into groups using your categories. So that's one move that you can make.
Okay, no, I found it on the Moodle thing. It says April 13th, 2025. So that's the right year at least.
Getting there.
Yeah, that's next.
I'm sure you'll have more questions about the mini project, but it is only 5% of your grade. Use it for fun.
Is that information included in the final exam? Those chapters, they want
Yeah. Yeah.
everything to rectify.
Everything, the whole course. But I will focus on this numerical data analysis on the final exam, right? Because you haven't been quizzed on it. And it's arguably kind of the most important.
Yeah,
So.
just, you know,
Definitely. Yeah, because you're basically making yourself a practice final exam. Yeah. Yeah. I guess, well, this is just me having ideas on the spot. I guess what I could do is I could take questions from your mini projects and make it the final exam.
no.
Thought it was a good idea.
Interesting idea.
It's a fun idea. You can share all your questions that you've made.
For the next
No, we
group.
will need to sign.
Yeah, for the next group. Fair enough. Fair enough. We'll put it on next year. Yeah. Can only innovate so much, right? Okay.
This kind of class again next year.
I hope so. I hope I get it. I don't know what I'm teaching yet next year, but it'll run next year, but
Oh,
they just tell me what to do and I go do it. Yeah. Okay, so yeah, if you have any questions, I'm sure you'll have more, but let's get crack-lacking on chapter 20, which is our second to last chapter because I slashed a few. Oh, okay, this is more of a favor. I created an assignment, a video assignment on statistical process controls, which would have gone way back with regression, but it is about, you know, when is a process in control, out of control, and how do you determine those bounds? And so it's for a different class, but I'll post it for you guys, and if you want to do it, I'll use it as a bonus assignment, just because I need to see if there's any issues with it. And if there are, let me know.
That's just the control part where you pick your mean and then do one,
Totally.
-2 and then 3.
Yeah, yeah. And so I think you guys kind of know what it's supposed to be already, whereas my other class, they won't ever have seen it. And so that's why I thought, wouldn't it be nice if I could get some feedback from you guys? Yeah, right?
We're about to have it on our LinkedIn, sure.
So you guys are the perfect candidates. I'll make it a bonus assignment. So then if you do it, it'll replace a lower assignment grade. And so there's going to be a SPC, a statistical process control bonus assignment. And I am looking for feedback on that, if there's anything that's kind of misbehaving, or obviously I've done my own testing, but it's better to have a big group kind of run through it. Okay? And so how it's set up is it steps you through a video and then it'll pause and make you do the same thing, and then you watch the rest of the video, or a little bit more of the video, and then it pauses and you do that in the next question, and so on and so forth. So for feedback. But I'll make a note on that assignment as well. Okay, so one thing that I do often, I don't tend to do it, well, I haven't done it with you guys, but in my bigger classes, I always have 2 versions of a test. Okay? I know, and I'm mean, and I make them look exactly the same. And I don't even tell them on the first one, and then they know. But it's more for my curiosity. And so one of the concerns that I would have if I'm creating 2 versions of a test, now I only change numbers, and so that, you know, shouldn't really impact the grades on the versions. But one main concern that I would have, and what I always check, is the mean, right, significantly different, or the mean grade or the average grade on these 2 versions, are they significantly different from each other? That would be a concern for me, right? So then I'm always hoping that they're not significantly different from each other. And so that's a similar example, but she's got numbers ready to go here, so that's cool. And so the scenario is this, but I do it all the time. And when I do have 2 versions of a test, I do a t-test to make sure that they are not significantly different. But an instructor decided to run two slight variations of the same exam. Prior to passing out the exams, they shuffled the exams together to ensure each student received a random version. Anticipating complaints from students who took version B, they would like to evaluate whether the difference observed in the groups is so large that it provides convincing evidence that version B was more difficult on average than version A. And so now we're talking about a difference in these two versions and in the grades, which would be a numerical variable. And so what we have is we have version A, version B, different sample sizes, 58 and 55. That's okay, we can handle that. Okay, our test statistic will be able to handle that. I've got a mean of 75.1, which is higher than 72. Okay. We want to know if it's significantly higher than 72. Okay. And then we have the standard deviations, which are essentially the same. We also have the minimums and the maximums, which might be interesting, right? The maximum for both is 100, but the minimum is slightly higher for version A. Okay. Okay. So now I have two groups. Right, I have two sample means. And so what we do, just like we did with proportions, is if we want to compare these two sample means, then I look at the difference between them. Okay. And so we want to compare mu1 and mu2. I guess I should use A and B, but I fear I'll slip up. Mu A and mu B, right? Population mean of group A and the population mean of group B. Now here I have samples from each of those populations. Okay. And so what we do is we will analyze the difference mu A minus mu B. We need a point estimate. Okay. And so what's my point estimate? My best guess at mu A is going to be X bar A. So my point estimate of this thing, my best guess, is going to be X bar A minus X bar B, right? Sample mean of group A, sample mean of group B. But just like we saw with two sample proportions, right now I have information from both groups. And so I need to incorporate all that information. Okay. And so the central limit theorem says this, says that X bar A minus X bar B, and that's one thing, difference, follows a normal distribution. And it's going to be centered on mu A minus mu B. With a standard error of sigma squared A over NA plus sigma squared B over NB square rooted. I'll make these. CLT is the central limit theorem. But just like before, we kind of ignore this, but this is why we're able to use the formulas that we have, right? This looks familiar, except I don't have sigma, right? Sigma is the population standard deviation. I don't have mu, I have X bar, right? And so now we're replacing these two things, but really what's going to happen is we create a T, and T behaves the same way as it did last week, right? And as it has for the past hundreds of years. I guess we have conditions, right? The central limit theorem, right? We're leveraging the central limit theorem, but it only really applies if the conditions are met. Okay. So the conditions for the central limit theorem, we need independence. If your samples were random samples, right, or in this case, randomly assigned in an experiment, okay, but as soon as something's randomly sampled or randomly assigned, we can assume independence, okay? And so if both samples were randomly assigned or selected, we may assume independence. I didn't make you check the conditions in the mini project and it's too late now. Already committed. That's okay. If both samples were randomly assigned or selected, we may assume independence within each group. But now I have two groups and I want to compare the two as if they're independent, right? And so now I also need the two groups are independent of each other. In terms of normality, right? The second condition is the normality condition. What's nice for means questions is that we just need to have a large enough sample size, right? If n for each group is bigger than 30, then we can assume normality, right? And so if n is greater than or equal to 30 for each group, we can assume normality. Just like we talked about last week, if your n is less than 30, that's okay. You're allowed to have small sample sizes, but you need to dig a little bit deeper and make a histogram and make sure that it looks approximately normal, right? And you can be a little bit flexible there. Okay, kind of, if I collected a larger data set, I suspect this would approach a normal distribution, something like that, right? Fill in the gaps. So if n is less than 30, we would need to make a histogram to ensure that the distribution looks approximately normal. We would need to make a histogram of each group to ensure the distribution looks approximately normal. Approximately normal. And if it doesn't, you're out of your depth. And that's okay. But it will. You can usually argue that it looks approximately normal. For us, right, here, the each student received a random version, right? So the versions were randomly assigned. So we can assume that these are independent, right? Observations within each version are independent of each other, but also the group that wrote version A versus version B, there's no reason to say that they're linked in any way, right? And so we have independence on both within and between, okay, the groups. So for our example, just to get the conditions out of the way, versions, well, I should label it conditions, independence, versions were randomly assigned so we may assume independence within the versions. Independence within the versions. And students writing version A versus writing version B, we assume that they're independent of each other. Students writing version A versus version B can be assumed to be independent. Of each other as a group. They've done studies, obviously there's a lot of studies being done in education, and even if the two tests are exactly the same, but you put a different color on the front cover and you say, oh, if you got the pink cover, then yeah, that one's really hard. And that actually does yield a significant difference in the grades. So don't let it psych you out. If I tell you that one's harder than the other, it's not true, right? So, but we can be influenced in that way. Okay. What, I got the hard one? Ah. For normality, right? Our sample sizes are big enough. And so we have a sample size of 58 and 55. Both of those are greater than 30. So we can assume normality. And the A was 58. Yeah, and 55. Which is greater than or equal to 30, and B, which was 55, is also greater than or equal to 30. So we may assume normality. Okay, so I'm comparing these two means, right? My hypothesis has to be about how does mu A compare to mu B, right? And what we said in the two sample proportions case is we're going to look at the difference between the two, and that's what we're going to do for means as well. And so for our kind of step one in general, step one is state the hypotheses. Oops. Oops, X, jumping ahead. H naught is a statement. Okay. And what we're going to do is we're going to talk about just in general how mu1 minus mu2 is equal to 0. I'll do a question specific one with mu A and mu B. Or if you prefer, you could have mu1 is equal to mu2, right? Add mu2 to both sides, and then you have mu1 is equal to mu2. I find that that one's easier to look at, right? But just like in the proportions case, right, this is the shape of our point estimate, and so it makes more sense to me to kind of introduce it this way. But if you prefer to write it this way, right, mu1 is equal to mu2, I have to assume that these two averages are the same until I have proof otherwise. Okay? You're allowed to do that. Mu1 minus mu2 is not equal to 0, right? We'll have a question specific one. Or mu1 does not equal mu2. And of course, the sign in the alternative hypothesis not only determines what your p-value needs to be, if it needs to be one-sided or two-sided, but it also depends on the question, right? It can be less than, it can be greater than, or it can be not equal to. This doesn't look. So for our example, step 1, my null hypothesis, and just like in the proportions case, you have to have question-specific subscripts, right? Especially if you're comparing mu1 and mu2, one's less than the other, then having a generic mu1, mu2 doesn't tell me anything, right? You have to have, must use question-specific subscripts. Which doesn't really change much for us in our example, but we would have mu a minus mu b is equal to 0. Or if you prefer, mu a is equal to mu b, right? We assume that the average grade on these tests are the same until we have proof otherwise. Now, we wanted to know if the average on version B was less than the average on version A. Okay? And that, when I write my hypothesis like this, right, then I have to figure out, okay, how would that difference relate to 0? Okay? Whereas I think it's a little bit easier if you have HA mu A compared to mu B, right? You wanted to know if mu A was greater than mu B, right? So then you'd have the mu A is greater than mu B, right? It's easier, I think, to see that and to look at it as opposed to here. If mu B is less than mu A, right, then I would get a positive value, right? Think about 3 minus 2, get 1, which is positive, right? Versus 2 minus 3, which would be negative, right? So you can always kind of plug in values, and this should be is greater than 0, right, in this example. Because we're only concerned if version B has a significantly lower grade than version A. This makes it a one-sided test. Right, I'm only concerned with one extreme. Nice. How about step 2? Do the test. Do the do. What I really mean is calculate the test statistic. What is our test statistic? For 2 sample means, if you want to compare them, right, we take our point estimate, and spoiler alert, it will be a t, which is really nice because we know how t behaves already. But my point estimate is going to be x1 bar minus x2 bar technically minus mu1 minus mu2. We've seen that before though, in the proportions case, because if we assume our null hypothesis is true, then mu1 minus mu2 is 0, right? And so this, our null hypothesis says that mu1 minus mu2 is equal to 0. And we assume that's true. So what are we technically looking at? We're looking at, okay, well, how far is this difference from 0? Right? But we need to take into account the spread, right? Those standard deviations. So then we bring in the standard error of the point estimate, which is this mumbo jumbo here. But we don't have sigma, so we use our best guess, which is our sample standard deviation. Right? Make sure you square those. So the standard error of this thing is S1 squared over N1 plus S2 squared over N2 in general. Huh? You have your sample standard deviations, you have your sample sizes, right? And usually on the formula sheet, I don't even write this part, but do you want it there? Seeing a mixed bag. Yeah, I find it's confusing to see it there, but just it goes to 0. So maybe I'll just exclude it and only have this top part that we need. But technically you are seeing how far is this difference from 0, taking into account the spread. Okay. For our example, step 2, do the test. What's really nice is in Excel, there's a t.test function that you can play around with. It requires the data, which we don't have in this case, right? And so what it does is it takes sample 1, sample 2, and it does all the background math. And I am pretty sure, if I'm not misremembering, it returns the p-value, potentially. Can't remember. Play around with it. Okay. I'll grab just the information we need here. X bar A minus X bar B. How far is it from 0? SA squared over NA, oops, NA plus SB squared over NB. You've got your means, you've got your standard deviations, you've got your sample sizes. I think we're ready to go. I get 75.1 minus 72.0. Now, it doesn't matter which group you treat as group 1 and group 2, as long as you're consistent, right? You don't want to be jumping around. So in theory, you could have had version B as group 1 and version A as group 2. Feels weird. I don't tend to do that. I just tend to do it in the order that they appear. But the only thing that would change, right? What would change if we look at this, right? The standard deviation of A over the number of the sample size of group A, right? Or squared standard deviation over the sample size, that would be the same. And even if I swap these, right, I would get the same standard error. So the only thing that changes is your the sign of your t, right? And it would just put you in another in the other tail. Yeah, but then you'd have to change your alternative hypothesis to match how you calculate the difference. Right? Divided by the square root of 13.9 squared over 58 plus 13.8 squared over 55. My calculator. Oops. 75.1 minus 72. Let's start there. I get a t of 3.1. 13.9 squared divided by 58. I'm going to store that. Squared divided by 55. Let's recall A. Make sure you don't forget to take the square root. Square root of 6.793752351. Square root that. $2.60648275. Now I suspect at this point you've come around to maybe not using your calculator so much and just letting Excel do it, right? Reference all the cells. I know you have. You love it. 1.189342225. Well, my gut reaction is, phew, why? That's not very far from 0, right? T is centered on 0, right? And so I kind of, once I pass 2, then I start to reject H0. Rejecting H0 in this case would be really bad for me, right? It would mean that there's evidence that version B was significantly harder than version A, right? And so here, right away, whew, what a relief, right? But we follow it up with the p-value. Okay. So let's see here. Step 3, find the p-value. Depending on your alternative hypothesis, right? T is always centered on 0, right? But you're going to have your test statistic, your T is going to be somewhere maybe in the upper tail like ours is, right? So then your one-sided p-value is the area in the upper tail, right? If your alternative is that mu A minus mu B is greater than 0. Versus if your alternative hypothesis was that mu A minus mu B, I guess I should have used 1s and 2s and this is less than 0, then your test statistic would need to be in the lower tail, right? It would need to be below 0. So then your T would be somewhere down here, which means this area here is your one-sided p-value. And if you have not equal to, right? Still centered on 0. If the alternative hypothesis is that mu A minus mu B is not equal to 0, your test statistic is only going to happen in one of those tails, right? But then you're equally concerned if it were to happen just as far away on the other side, right? And so here you'd have your t and a negative version of t. Then you'd have to find the area in the two tails. So this makes your two-sided p-value. Now, t-tests are a lot more common than z-tests for proportions. And so in Excel, right, you have a t dot dist dot 2t, I think it is. So here you'd have t dot dist dot 2t, right? And it gives you, it takes the t and the degrees of freedom. Pretty sure. If you want the upper tail, now I'm just going by memory, but I'm pretty sure there's a right tail, right? So a t dot dist dot rt. Of t and the degrees of freedom. Right? Or you can always just use t dot dist, which behaves the same way that we've been using it, right? But if you want, it'll only give you the area to the left, right? Then you'd have to do the 1 minus thing if you want the upper tail. You'd have to multiply it by 2 if you want both tails, right? But you can always just use the t dot dist. But what's nice about Excel is, and a lot of programming languages, is you start typing what you think you might need equals t, and then you just kind of wait for it to populate and see what your options are. You can kind of scroll around. Yeah. And so the only one you really need is this one. Right. If you have the raw data, try equals t dot test. And I can't remember what the arguments are. So I'll do dot dot dot. I think it takes array 1, array 2. I'll put it in your assignment for today. Arrays. Okay.
Practice and mother arrays now.
Fancy. These all require the degrees of freedom. So what are the degrees of freedom? The degrees of freedom for 2 sample means is way too complicated for us to bother with. And so what we do is we use a more conservative estimate of the smallest sample size minus 1. Womp womp. I know. It's like this huge formula that Excel would use in the background. Okay. And it is proper, it incorporates the standard deviations, blah, 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 blah. But for our purposes, conservative.
So the version is the t though, right?
Yeah. But off the top of my head, can't remember what the conservative part of it is. I think it has to do with the variances, right?
It's the fact that we're choosing pooled versus unpooled variances. And we chose unpooled here, so it feels weird to choose an unpooled variance for T naught, but then go back to the pooled version of the T, but not even the right one.
It's all the same. Yeah. And I think if you use the T dot test, it'll ask you for if you're assuming equal variances or not. Yeah. Okay. It's okay. Don't worry. Don't. Degrees of freedom, right? We need our degrees of freedom. Technically, huge formula that you would never need to do by hand. And so, because it's pretty recent that we even had software to do this stuff. And so, technically, a big formula that Excel will use in the background if using the t.test function. But for us, we're just going to use the smaller sample size -1. That's fine.
Yeah, I've got a question, Matt. Like, it feels like you have more degrees of freedom than that because of the fact that you have both N1 and N2, right?
You do. But the only thing that's going to happen is you are reporting that you have less reliable results than you actually do. And that's fine. That's better than the other way, where you're pretending to have more reliable results than you actually do.
Gotcha.
Yeah. So yeah, so we're just lifting the tails a little bit and saying, we can use software if we want to. We will use the smaller sample size -1, which we usually write out like this. It's the minimum of N1 -1 or N2 -1. Minimum function takes the smaller of the two values, right? You can calculate N1 -1, you can calculate N2 -1, right? And then take the smaller of those two, and that will be your degrees of freedom. So in our example, step 3 is find the p-value. My degrees of freedom is the minimum of NA -1 or NB -1, which is the minimum of 58 -1 or 55 -1. Stack these. The minimum of 57 or 54, the minimum of those two is 54. So my degrees of freedom, I have 54 degrees of freedom. Right. There's lots of other kind of degrees of freedom approximations that you could use, but we're going to use this one. You could do a N1 plus N2 minus 2. But this is the most conservative estimate, which is fine. Now what? In Excel, we need to find our p-value. Now we have, that mu A minus mu B is greater than 0. Right? Which means that I need the area in the upper tail, right? Because I want to know if it's significantly above 0. Okay? And that makes sense because I found a positive t as well. Okay? And so my t is 1.189, let's say. T is still centered on 0 and T is 1.189. And the area in the upper tail is my one-sided p-value. In Excel, you can use equals, T dot dist dot right tail of 1.189 and 54 degrees of freedom. Let's see, where's my trusty Excel here? I keep adding to this random sheet here. I'll start a freshie. Okay. Equals T dot dist. Coming up with just T dot dist, which you can absolutely use. It works the same way as the norm dot dist, right? Where you have to do the 1 minus if you need to, which we would. But I also have the right tail, which saves me that one minus step. And so I'll use that. It needs the X, which is my T, which in this case is 1.189. And it wants the degrees of freedom, and we're going to use 54. I find, let's screenshot this. Oof. That my one-sided p-value is 0.119821. Therefore, let's see here. 0.119821. This is my one-sided p-value. Now I can use this to draw my conclusion. We use an alpha level of 0.05 unless there's, a lot of risk in if you made a type 1 error, right? Type 1 error is if you reject H naught, but you shouldn't have, right? If that's very expensive, then, and I can mean expensive in a lot of different ways, right? Financially or kind of morally or ethically or whatever, right? And so if it's expensive, then you'd want to use a lower alpha level, right? And so, but we'll just use 0.05 across the board, right? There's no reason to adjust it. So now I have my one-sided p-value, which is what I want. This is the probability, right? It's the area under the curve, so it's a probability of seeing a difference in the mean scores as different from 0 as we saw, assuming that the true difference is actually 0. Right? And so the conclusion, step 4, do you want the generic conclusion? So same as always, but it might be nice as a refresher. Step 4, conclusion. If the p-value is less than the alpha level, we have enough evidence to reject H naught. we have enough evidence to reject H naught. If you're rejecting it, you can offer up HA, right, in favor of HA, but in general, I'm fine if I never see HA in your conclusion, right? Usually we do, just if you've rejected H naught, then you say, in favor of HA, right? But that's the only time that it would come into play. Yeah. Versus, or, I guess I should say, and I'm gonna copy this so that you can see the symmetry. If the p-value is not less than the alpha level, right, we do not have enough evidence to reject H naught. Those are your only two options. Your conclusion always has to be in terms of the null hypothesis because you did all your testing assuming that it was centered on 0, right? And now we have evidence that, okay, that seems reasonable enough. Yeah. So for us, for our example, right, we show off a little bit more because we have more information for our example, right? If the p-value is less than the alpha level, well, you should compare the two, right? Since our one-sided p-value of 0.11 blah, blah, blah is not less than our alpha level of 0.05, right? So just incorporate those numbers. Oops. Since our one-sided p-value of 0.119821 is not less than our alpha level of 0.05, then our alpha level of 0.05, we do not have enough evidence to reject H naught. We do not have enough evidence to reject H naught. Would your p-value, how would your p-value change if we decided to do a two-sided test? If we were doing a two-sided test, so mu A is not equal to mu B, right? Or mu A minus mu B is not equal to 0, right? Just different. Then you would take this p-value and you would multiply it by 2, right? And you would be just as concerned if it happened on this lower end. Okay, so that would make your p-value even bigger, right? And that's why we generally prefer to do two-sided tests, is because it makes it even harder to reject H naught when we shouldn't, right? And it just makes it a little bit safer. In this case, we're already failing to reject H naught. So, but just remember, the only change if you had a two-sided test, you would multiply this by 2, right? Replicate it in the other tail. Okay, this means, therefore, there is no evidence that version B was more difficult, I think it was. But really how we're gauging that is, I'll clarify here. That is the mean grades on version A are not significantly less than version B. The mean grade on version B is not significantly less than the mean grade on version A. just because I want to bring it back to the means, because we're analyzing two means and how they compare. Time flies, slipping through my fingers. Confidence intervals. You can build a confidence interval because the standard error is going to be the same. Okay? And so, but any questions about the hypothesis test? Right, the hypothesis test is the meat and potatoes of what we do. But if we did find that there was a difference in the grades, then we would be curious, okay, well then what is a reasonable difference for the grades? Do you expect the confidence interval to include 0? The confidence interval for the difference in the means? In this case, yeah, we do, because we just said there's no evidence that it's anything but 0, right? Or significantly different from 0. So confidence intervals for mu1 minus mu2. Any confidence interval, right, has the format of the point estimate plus minus a critical value times the standard error of the point estimate. We have all those things, right? The critical value in this case is going to follow a t distribution. Okay. And so what we have is, in general, we have x1 bar minus x2 bar. Right? The difference in my sample means plus minus my t star, right? That's going to be the t that captures the central 95 or 99 or 90% of the curve, right? And we use that t dot inverse command at still the minimum of n1 minus 1, n2 minus 1 degrees of freedom. And the standard error we're going to use is s1 squared over n1 plus s2 squared over n2. What's nice is in your hypothesis test, you would have already calculated that standard error. And now you can just reference it again, right? Especially if you're working in Excel. Or you can store it or whatever. So here we use the t dot inverse, and I think there are a couple of different options. Let's see. We're gonna start typing. You got an idea of what you want to do? T dot, and we've got inverse and two tail, and then the t dot test, which I encourage you to poke around with. But it does require the data set, which we don't have in this case. Let's do the t dot inverse. You can use the two tail, but let's keep it back to basics. Should we make a 95% confidence interval? Pretty standard stuff. Right? Then the probability is going to be the area in one of the tails, right? And I'm pretty sure the t dot inverse dot two tail takes the area in two of the tails, which you can play around with. But for a 95% confidence interval, I have 5% left over, split evenly amongst the tails. So I have 0.025 in the lower tail. So I'm going to force that 0.025. And we are going to use 54 degrees of freedom again. Sorry, I should have warned you. It's close to 2, which is what we would expect for a 95% confidence interval. Come on. I want to zip it up. T dot inverse of P, or I guess it says probability. And the degrees of freedom. For a 95% confidence interval, the probability is 0.025. Right? Because T is still centered on 0, but between these two values, you've got 0.95, which means you have 0.05 split evenly amongst the tails. 0.05 divided by 2 is 0.025, and 0.05 divided by 2 is 0.025. This is going to give you a negative T star, and this is going to be your positive T star. So you could have used 0.975, and then you would have had the positive value here. Right? We have a negative. It doesn't do anything, or it doesn't really make a difference. It just changes your plus to a minus and your minus to a plus, which is actually kind of how you tend to want to do these calculations anyways, right? So it's kind of convenient. Yeah.
Is the 1.96 more or less accurate?
1.96 is for a Z, and the T distribution approaches a Z distribution, but only once you've collected the entire population, which is kind of, yeah, not gonna happen. So the T is better to use, but it allows for more wiggle room.
Gotcha.
Nice. Okay. So for our example, I'm racing the clock, I know. Construct 95% confidence interval. Oh, and I guess this can go. For the difference in mean scores on version A versus version B. I guess I should say and version B. We take our difference, right? We have XA bar minus XB bar plus minus T star at SA squared over NA plus SB squared over NB. Put a little crook on that. Let's see if I can remember. I cannot. Gonna copy these. Copy. But these are both components that you've calculated already in your test statistic, right? And so you can recycle those if you've got your cells all made up. 75.1 minus 72 plus minus, and then this little guy is going to go over here. T star is 2.00488. You guys love rounding stuff, but if I get something that's precise, I'm going to use it. You should too. I know we could get more decimal places, and if you use Excel and you reference those cells, then you'd be able to use them all, right? Okay, 13.9 squared over 58 plus 13.8 squared over 55. Now, if I'd been clever, I would have stored that already, but I didn't. 13.9 squared divided by syntax error. No. .8 squared divided by 55. Square root that. Yeah. I'm gonna times that by 2.00488. I have a margin of error of 5.225685145. I'm gonna store that. I have a difference of 3.1 still. So 3.1 minus that little guy, I get negative 2.125685145 up to 3.1 plus that little guy. That little guy is the margin of error. 8.325685145. And we have to interpret this thing. And the interpretation stays the same as always. Just remember that it's about the difference in the mean scores now, right? And so because the difference crosses 0, right, then they're all crisscross applesauce and they're basically the same. Technical term, I know. We are 95% confident the interval from, let's say, negative 2.13 to 8.33 captures. Now, it's really important that your confidence interval is not, it's not a probability, because the difference in the true means, so in the population means, is fixed. It exists, we just don't know what it is, right? And so the 95% confidence comes from our samples being unreliable, right? Or potentially unreliable. Okay. And so we're 95% confident that the interval from here to here, negative 2 to 8, captures the true difference in mean scores on version A and version B. Ta-da! Did it. So that's 2 independent sample means, and on Thursday we'll do paired data, and then you're all done, sort of. If you have any questions, let me know. Good luck on your test. See you on Thursday.